This is a quick review of time series, and these are mostly my notes, and I'm recording this so that I can listen to it at a later time, and not exactly recording for other people, but if anybody else benefits, that's great. So a series is a any collection of data points, but if those data points are indexed by time or date, then you can call them as time series. So each value that you're recording, for example, if you're considering temperature, you can say temperature of of last week. So each temperature that you collect has a data associated with it. So that becomes a time series. You can think of sales, same thing, like what happened on the sales last week, last Monday, last Tuesday, last Wednesday. So you're associating a time to a data point, and that becomes a time series data point. And forecasting is one of the important applications in many businesses because you have to do resource planning, you have to probably allocate enough number of people, capacity planning, and so on, are based on the forecast. So time series and forecasting is one of the important concepts in data science, and historically there is some models that have been developed in statistics, and we are going to look into that along with some modern ways of doing forecasting. So if you are given a series of data, before getting into the details, I think there is an open source book that's a time series, and this the forecasting principles and practice, and this is one of the really important book to go through, and it's available online, and it's o texts. You can purchase it, but also you can access it online. So this most of the material that I'm covering here, images wise, are coming from this particular book. So the first thing is that whenever you are given a series, you can decompose into a trend, seasonality, and error. For example, in this case, you have an observed data looks something like this, and then you decompose this particular series into a trend and then also a cycle. Maybe this is 2010, so probably yearly cycle, and so on. So this is a seasonal component, and then whatever that's not coming into each of these is irregular, so or error. So you can decompose into these things, and there is a confusion about seasonality and cycles. Seasonality usually refers to something that happens within a specified time during a year. You can say, winter, you can say Christmas is a season, you can say July 4th is a season. So it comes at exactly the same time, around the same time. Whereas cycles, for example, recession could be considered a cycle. Usually it is said that recession comes every 8 to 10 years. So that's actually a longer period, extending most of the time the data period that we are looking into. And these cycles don't have a predictable time period. Sometimes it can come in 8 years, sometimes 15 years, and so on. So it's not very predictable, but so that's the difference between seasonality. Seasonality we can predict exactly when the dates, like July 4th comes at the same time every year. So that's a seasonal component, whereas cycles are long term. So that there are, if you want to forecast or if you want to understand, let's say somebody asks you what is the weather tomorrow, I can easily say, okay, today is 70 degrees, so maybe I could easily say tomorrow will be 70 degrees. You will not be wrong, but maybe if I want to, let's say, be a little bit more accurate, and maybe yesterday it rained, so maybe this is a rainy season, and I want to incorporate past 4 days, and that's a simple averaging, and I average last 4 days temperature, and give a prediction or a forecast for tomorrow's weather. So that's a simple moving averages. But an exponential weighted average is something where you're weighting the importance of which data point. Like the most recent one, for example, has more importance. For example, I could weigh more yesterday's temperature compared to like 10 days ago's temperature. So that's a exponential weighting, and then that's determined by a smoothing parameter known as alpha. So Holt's method is an extension of this exponentially weighted smoothing method, where he also looked into a trend along with regular smoothing, a trend component as well, where trend is, if you looked at here, it denotes a trend, which means it's going upward direction, so that indicates a trend. So even for trend, you can you can do smoothing functions for trends as well. And so that's a Holt's method. There is also seasonality. If you do smoothing function for both trend and seasonality, then you could consider Holt's winter method, right? It's a level as well as seasonality. It's level, trend, and seasonality. Level is like a plain data set without considering other components. So this term AD is a additive damped. So when you're doing a forecast, if you stretch out too far, the trend doesn't maintain. So you would rather want to damp it down after a certain time, so you can put a damping component and it gives better results than directly using a trend component itself. So that's a damped trend. And if you generalize this form, you will get a many combinations. So for example, here in this book it says taxonomy of exponential smoothing methods. You have a trend component which can be additive damped. There is also a multiplicity component which I did not put it here, but in the models actually you can find it. And for seasons you can have no season, or you can have additive season or multiplicative season. So even in trend there is a multiplicative component, which we are ignoring, but you can see even with these three things you have about nine combinations. With the fourth one you could probably expect 12 combinations. So each one has a name. Holt's linear method, where you're only looking at the trend, you can add additive damp. So if it's both additive or multiplicative trend and season, then it's an additive Holt's winter method. So this has both trend as well as season. So this is a generalization of Holt's winter method, and that covers exponential smoothing component. So the other way of looking at is this is a decomposition way of looking at things. Then this one is a regression, auto-regression way of looking at things. So one of the important component to understand is what is stationary and what is differencing. So stationary defines it says its property does not depend on the time at which series is observed. So and maybe this is not easy to understand, but you can think of like time series with trends and seasonalities are not stationary, or in other words, time series with no trends and with no seasonality is considered as a stationary series. So in this case, you can see some linear trend here, you can see a linear trend here, linear trend here. So you can ignore these as this can be considered as non-stationary. These has some cycles, like it looks like a cycle, so you can ignore this one. This one also looks like a cycle, you can ignore this one. So in this case, the B and G are considered, this B and G. Even though it looks like a cycle, I think it looks like a seasonal. This is not very consistent, right? So you can see also these extend beyond many years. So this cannot be considered as a seasonal trend. So B and G are considered to be stationary. Everything else has a trend, trend or seasons. So stationary, we need to make sure that before applying this auto regression or MA, we need to make sure that the series that we are applying these are stationary. And to obtain stationary series, we can do a differencing. So you can take, for example, if you have a series like y1, y2, y3, so you make the difference of y1 and y2. Now you have a d1, d2, d3, d4, d5. So this is the new series which is differenced once. But if you also difference one more time, d1 minus d2, d2 minus d3, and so on, that's a second order difference. So at each level, you can look at the graph and you will realize that by differencing, you can achieve stationary. So let's look at if we can find something. So in this case, this is a series, and you can see there is a trend. And as soon as you difference, you don't really see any trend here. So that's it's a by differencing, you are making the series a stationary series. So auto regression is you when you think of regression, it's one variable versus many other variables, whereas auto regression is one variable and it's previous values, previous days values. For example, today's temperature against yesterday's or day before yesterday's. If you're regressing, that's auto regression. And how many days back you go is the order of the auto regression. In this case, p, for example, if you want to consider yesterday, day before yesterday, and the day before, then the order will be 3, right? So if you only consider yesterday, the order will be 1, and so on. And then moving averages. So this is different from simple moving averages. So they are very different. So this is a regression containing values from previous ones. This is a regression. In a way, regression equation, it's a linear combination of errors. So the amount that we could not guess is the error, and if you combine them, that becomes moving averages. How many errors, how many days back error that you're looking at is considered moving averages, and the q is the order of moving averages. So let's see if I can so you can see this is auto regression. So your yt is a linear combination of previous day, the day before, and so on. And if you have p component, then you go all the way to y minus p. So whereas moving averages is error at time t that you could not guess what it was, and then error at time t1 multiplied by again linear combination of until t minus q points. So this is the moving average model. And a generalized model of both AR and MA is ARIMA. So AR is auto regression and MO is moving averages, and I is integrated differences. So that the differences, for example, if you look at the stationary, to make the series stationary, we have to difference the data set quite a few times, and that is the component that is D. So again, if you look at P00, that's AR, and 00Q, that's MA, and there are two kinds of plots known as ACF, autocorrelation function, and partial autocorrelation function plots. These can help if an expert can actually look into these plots and determine what the P could be based on PACF plot and what Q could be based on ACF plots. So these plots are quite useful, and let's see if I can. So for example, this is ACF plots. It's a correlation of the first day values against the lag one. The if you take today's temperature and do a correlation against yesterday's, and then the day before yesterday's, and so on. So this gives a autocorrelation, but the lag, like yesterday, the lag, for example, consider this lag. It also has a component that indirectly contributing to this lag and also this lag. So that's and also the towards today's temperature. Whereas this lag is its independent component, whatever is contributing by this one because of this one, is ignored. Only independent component from the this lag is captured. So that's a partial ACF. It's a direct contribution of itself, not an indirect. Whereas this one ACF is a direct and indirect contribution towards today's value. So these values can be useful to compute P and Q. But there are other ways you can do auto arima. Like there is a package called PMD arima. You can call auto arima, and it will try to iterate through various P and Q values and come up with a best value for those. So you don't have to rely on ACF and PACF plots, but it's good to know that these are helpful. There's also Granger causality test, which is used to know whether there is a causality between two series. Another important test is stationary decay Fuller test, or ADF test, and that test can indicate whether a certain series is stationary or not. You can look at the p-value and determine whether that series is stationary or not. Even more generalized version of ARIMA is a seasonal ARIMA, and X is even further generalization, which is exogenous variables are allowed in this one. So let's look at SARIMA, which is ARIMA but with seasons. So you have a PQD component for the trend, but also you have you have a seasonal PQD for season as well, and S is the length of the season. So this X that is there in SARIMAX is exogenous variables. For example, if you want to include holidays into the model, you can use SARIMAX. I'll also show the code so that it becomes a little bit easy to understand what these are. Facebook Prophet, and this is a newer way of it is an improvement over, in a way you can think of ARIMA, but it's a more of a practical approach rather than like a statistical foundation. So it does use some of the learnings from here, but these approaches can actually scale very well. When I say it's not foundationally statistical, the errors, for example, may not be considered as coming from IID, or when they present a confidence interval, they may not be presenting 95% confidence interval like in statistics and so on. But it's a very simplified approach and it's very easy to implement, and also look at the documentation. For example, if you look at the Quick Start API, it's fairly straightforward. You can just from Prophet import Prophet, and then you're reading some data set, and you're creating a model here, and you're fitting the model, and you're making future data frame, and then you can so it creates a DS. But remember that data is always represented as a DS and Y. These are the column names. That is the standard for doing the predictions in Prophet. And then you can do predict future. So it generates a data frame like the time series depending on the number of periods, and then you are predicting for that period. And then you will get when you do the forecast, when you say predict, you get y hat, also lower bound and upper bound for each of the dates that you have. So that's very straightforward. It all the details like the trend, seasonality, auto regressions, moving averages, and so on are all taken care underneath it. They approach it slightly differently and get to the solution. So you can see the plots and breakdown of components, yearly season trends, weekly and yearly seasonalities, and so on. And it's very easy to implement it. So some of the code is also here. So you can incorporate a holiday list as well, and it does two seasonal components, weekly seasons and also yearly season, and it calculates trends using a piecewise linear models. And the whole model is a generalized additive model, and each of these tries to capture one of these components. So the final one is neural networks. You can use RNN, RLSTM, and you can use XGBoost and regressor. So this is so the idea behind this one is you can take the date variable and do some feature engineering and create additional variables like week, day, hour, holidays, etc. And then based on the past, these variables can capture the trends or seasonality, and then they can be quite useful in predicting what will happen in the future. There are a few other basics like how do you split training and validation. So you don't take random points like the way train test split, but rather you up to certain time point you take as a training, and past that one you're using it for testing. So that's one thing that you need to do. And then usually evaluations wise, in time series, evaluations are done using either MSE or MAE or RMSE. So if there are outliers, MSE will look very big. If you want it to be sensitive to outliers, then maybe MAE is better. So these are usually used to do evaluations. But let's look at what all of these components, this decomposition, exponential smoothing, ARIMA and SARIMA, and Facebook profit, and the other methods, how does the code looks like. So it's a quick recap of the codes. So if you want to plot any like a pandas series, data series, you can create a figure, and then you can set the limits of start date, end date, and you can set the limits by y, and you can do a plot. So if you want to import certain data sets, and the statsmodel API data sets has some data sets, useful data sets that you can quickly download and look at the trends and try to learn from these data sets. So there are certain filters where you can break down into cycles and trends. This is different from seasons. Again, seasonal decomposition, there is a package in statsmodel known as seasonal decompose, and you can seasonal decompose. You just give the variable, and you can specify whether you're decomposing as a multiplicative approach or additive approach. And then moving averages, using pandas, you can do dot rolling, window is equal to 6, and mean. So it will compute like mean of 6 days going past to the start of the series to the end of the series. 12 is it is taking average of 12 periods. And then EWM is exponential smoothing. So it's also a pandas function, and it's weighing. So you need to give alpha here, but if you don't give beta, it will calculate using a MSE approach, and then it incorporates that and computes that EWM. And there are stats models as well, simple exponential smoothing SES and exponential smoothing as ES. So you can compute SES, that smoothing level is equal to alpha, and you can say fitted value that shift. This will give you a shifted exponentially smoothed value in this 1, 2. And also this is double exponential, which is a Holmes method, where you have a level as well as trend incorporated. In this one, you can just say exponential smoothing, and you're giving the variable that you're looking at, and then trend and multiply. So the difference between this and this is you're saying simple exponential smoothing and your exponential smoothing. And here you're doing a triple exponential smoothing in a way. So you're adding trend as well as seasonal, and then you're specifying how the length of the season. So this is exponential smoothing with trend and seasonal periods. So the difference thing that I mentioned to we can either do that diff using like a pandas way, or you can do a difference between 2 days temperature and 6 days back temperature, and from stats model. So also you could use difference function from stats model itself, where d underscore k indicates how many lags do I need to look into, or actually how many times I need to do the differences. So periods is specifies how far I need to go back. Okay, forecasting, essentially you just say forecast is equal to fitted model. So you do exponential smoothing, and then you fit the model for number of period that you are interested in. So it's a, and ACF and PACF plotting, you can simply import these values, ACF, PACF, and then you can simply fit using this method, and then you can plot these values. You can plot using plot ACF functions. Actual plot ACF and plot PACF will compute PACF and ACF plots. Yeah, so you have you can do also a seasonal plot and a quarter plot showing the seasonal trend. And again, you have ARIMA. You can do stationary test using @fuller_df, and you can download from statsmodel. Auto ARIMA, you can this is the package that's outside of statsmodel, but it's like a wrapper package which does use statsmodel and compute auto ARIMA. If when you say fit, it will show out what are the possible values for P, Q, and you're giving some limitations, restrictions and the bounds of what P can be, what Q can be, but this will provide summary with the AIC values, and you can pick the best ones to do ARIMA calculations later. So these are some of the packages you can get from sklearn, like mean square error, MAE, and also you can download from RMSE from Stats Tools. So Remax is another package within Stats model. So you can say, you can specify trend order, seasonal order, and fit it. So in this case, I'm not providing what X is, but this is essentially a Sarima model. And if it's a Sari max, you're providing exogenous variable. What is the exogenous variable? And you're giving order, season, and this is the number of seasons. Right here, it's 12, it's 7, and additional options are needed to fit this. So Facebook profit, we just looked at in the quick start. But we essentially just call model is equal to profit, and you fit DF, and then you make future data frame for however many periods you want, and you call predict, and the results will be ds y hat lower and y hat upper, and you can simply plot using model.plot, or model.plot components are also plot.plotly, so that you can interactively look at how the plots are. Finally, deep neural networks are RSTM or LSTM. So this is a very simple code where you may have to use a time series generator, where it splits the training data into series of like the length of the season, and what is the predicted outcome. It automatically does it. So when you're doing the prediction, you have to use the you predict one value, and you have to add to the test data set, and then you try to use those values to predict again. For example, if the season is 12, you're predicting 13th value, and the next time you're adding this 13th value and ignoring the first value, and using these newly created 12 data points, you're trying to predict the next one. So this is a little bit of a processing that takes, but essentially these are all the methods that are needed. There are probably many parameters that needs to be set properly to get accurate predictions, but this is the summary of all the methods, and this is an overview of time series basic. Again, this is a very quick review, and it's not meant for somebody new, but mostly for somebody who already know, but they want to review just the keywords about time series, and what is involved in doing time series analysis. So with this, I think I'll conclude and close this session. Maybe we will come with an example data set and go through one example that probably solidifies these concepts, as well as the coding that we have looked into.